Okay, so I'd like to welcome everybody to Gabe Goldberg's second lecture in the CUNY Set Theory Seminar. And he's going to give us part 2 of last week's talk on the HOD conjecture and the structure of elementary embeddings. Gabe, take it away.
So last time I talked about how the HOD conjecture can be characterized in terms of the large cardinal structure of the universe. So not exactly the...
So your voice is almost inaudible.
Oh, again, okay.
Yes.
Is this better?
Sometimes.
Sometimes, well, yeah, I don't know if it's better for my...
Last week, sometimes it was good and sometimes bad.
Oh no, okay. Well, I'll try to be better. Okay, so it's about the relationship between the HOD conjecture and the large cardinal structure of the universe, which is a little different from what large cardinals exist in the universe. I mean, more like how the elementary embeddings that exist in the universe of sets are related to one another. Okay, so the HOD conjecture essentially says if there's an extendable cardinal, then is covered by HOD in the sense of the Jensen covering lemma above the extendable cardinal. So every set of cardinality, at least the extendable cardinal set of ordinals, can be covered by a set of ordinals in HOD, or the extendable set at the same time. And this is the conjecture is that this is and so the relationship between this and the large cardinal structure of the universe is sort of theorem. One of the following are equivalent. This is a little bit roughly stated. Kappa is extendable. One, the HOD conjecture holds. And two, well, okay, I've got a comment in the chat. Okay. Two, well, it's something that has to do with the uniqueness of elementary embeddings defined from one. So you can ask, I guess, before I state two, let me motivate a little bit. If J 0 and J1 go from V to M, must J0 and the ordinals be equal? Well, you could ask if J0 and J1 have to be equal first. And the answer is consistently no, and it's consistent with all large cardinals. But maybe J0 on the ordinals is equal to J1 on the ordinals. And Wooden had proved that this is a consequence of the HOD conjecture. And so the point of this theorem was to show that this sort of structural property of embeddings is actually equivalent to the HOD conjecture, but it's not quite this one. So what it is instead is 2, which says it's the local version of that. So for all regular delta greater than or equal to kappa, for sufficiently large, so sort of local, lambda greater than delta, if you have two elementary embeddings, J0 and J1, from V lambda into some model M, so into a common model, well, I want to say something like they agree on delta, but you can't prove that, so you need a little bit of resemblance between the embeddings at delta to prove it. So J0 and J1 go into the same model, and J0 of delta is equal to J1 of delta, and the supremum of the image of J0 on delta is equal to the supremum of the image of J1 on delta, then J0 is equal to J1 on delta. So that's equivalent to the HOD conjecture. It sort of seems like something you could attack, unlike the HOD conjecture, which seems impossible to approach because this is just some large cardinal combinatoric stuff. It really should be the HOD hypothesis, but I didn't want to say anything about the HOD hypothesis. Thanks, Shoshana. Yeah, so to be perfectly formal, this should say the HOD hypothesis, and the HOD conjecture should be the conjecture that the HOD hypothesis is provable. I don't want to go there. Okay, so what I wanted to talk about today is a related theorem, which says that the uniqueness of elementary embeddings, not of a rank initial segment of V, but of all of V, is just provable in ZFC. So if you have two elementary embeddings, J0 and J1, from V to a common inner model M, then J0 and J1 agree on every ordinal. Another way to say this is that their restrictions to HOD are equal. And the reason Wooden was looking at that is that it's sort of a K-like property of HOD. Any two embeddings of K, at least if there is no inner model with a strong cardinal, are into the same model, they're always equal. Okay. So some more stuff about this. What did I want to say? Yeah, so you can't prove, again, J0 is equal to J1 because consistently there are normal ultrafilters U0 and U1 on the least measurable cardinal, such that JU0 is not equal to JU1, but the ultra powers are actually equal. So that you can do that by forcing. Basically, the simplest forcing, non-trivial, but preserves the measurable cardinal will do that. So it's the Easton product of Cohen forcings on a measure zero set will force this. But actually, another theorem that I'm not going to talk about much or at all after I state it is if kappa is extendable, then if J0 and J1 go from V into the same inner model and have critical point above kappa, in fact, J0 is equal to J1. So, so this uniqueness fact that you can't prove is actually true above an extendable cardinal. And it's extendable is probably the right large cardinal because you can't prove it from like a proper class of supercompacts. Okay, I think that's all I'm going to say before I go into the proof. So the outline of the proof. Yeah, there was one more thing. The theorem is really easy to prove if you assume J0 and J1 are definable from parameters. And I did that last time. Basically, you look at the least ordinal for which there are such definable embeddings, and you show that that ordinal is definable. And so, well, sorry, I'm not even going to say it again. But I did say it last time. And everything is going to go by reducing to the case where J0 and J1 are definable. You might ask, why are you even interested in these undefinable embeddings? Because you need all the only classes there are the definable classes. But the point is, I mean, it's sort of analogous to the case with the CUNY inconsistency theorem, where it's very easy to prove, even in ZF, that if J is an elementary embedding from V to V, and it's definable, then J is equal to the identity. So this is the definable CUNY inconsistency. It's a theorem of ZF. Well, it's a theorem scheme of ZF, and it's really easy. But the undefinable CUNY inconsistency is sort of a deeper fact that involves the combinatorics of the axiom of choice, and the so it's analogous, and actually I'm giving a new proof of the CUNY inconsistency here, because if you take J and the identity, they're both elementary embeddings from V to V, then the theorem that I'm about to prove shows that J is equal to the identity on the ordinals. And so J is actually equal to the identity because it can have a critical point. So this is a generalization of the CUNY inconsistency, and it's actually the combinatorics that go into it are sort of new, and they have new consequences for the CUNY inconsistency itself, which maybe I'll discuss, but probably not, because I've talked for 15 minutes without starting the proof. Okay, finally, so I'm going to outline the proof of the uniqueness of elementary embeddings on the ordinals. The first thing that we'll do is assuming the singular Cardinals hypothesis will reduce the uniqueness of elementary embeddings on the ordinals to the uniqueness of definable elementary embeddings. So ESCH, the eventual singular Cardinals hypothesis, states for sufficiently large singular Cardinals lambda to the cofinality of lambda is equal to 2 to the cofinality of lambda times lambda plus. What I'll show first is that you can reduce under this hypothesis the thing we're trying to prove to just the definable version. The way that goes is by actually reducing it to the case of ultra power embeddings. So definition, suppose J is an elementary embedding from V into an inner model. Then if A is contained in M, then the Skolem hull of the image of V and A is defined to be J of F of S, where F is a function in V and S is a sequence of elements of A. And I mean, only saying this if S is in the domain of J of F. So this is the definition of the Skolem hull, but it turns out it's quite easy to prove. It's equivalent to Wash's theorem that this is the smallest elementary substructure of M that contains J image V and all of A. The reason is that all the Skolem functions you need are in here. Okay, 2. J is an ultra power embedding. If there is some A such that M is equal to the Skolem hull of J image V plus just the single point A. In other words, everything in M is definable from elements in the range J and the point A. The reason this is called an ultra-power embedding comes from the following lemma. If J from V to M is an ultra-power embedding, then J is definable from parameters. So that's not why it's called an ultra-power embedding, but it comes from the proof. So the proof goes, I mean, I'm just going to sketch it, sort of basic. So fix a set X in V. Well, okay, so we're in this context where M is the hull of a point A. So fix an X in V such that A, this point that gives you everything, is in J of X, and let U be the set of all B contained in X such that A is in J of B. So this is the ultrafilter derived from this elementary embedding using the point A. And then the thing is that since everything is definable from A and points in the range of J, it's just going to be true that M is equal to the ultrapower of V by U, and J is equal to the associated ultrapower embedding. So in particular, J is definable from the parameter U. I'm not going to prove that, but it's pretty easy. So ultrapower embeddings are definable, and I want to reduce this uniqueness of elementary embeddings to the uniqueness of ultrapower embeddings. The way that goes is proving this proposition. Suppose you have two embeddings into the same model. Then there are embeddings, ultrapower embeddings. Sorry, this assumption is the eventual singular Cardinals hypothesis. Then there are ultrapower embeddings, I0 and I1 from V into some ultrapower N, and an elementary embedding from N into M, such that J0 is equal to K composed with I0, and J1 is equal to K composed with I1. So the picture is, you've got V and M. You have your two embeddings, J0 and J1, and then you can find this model N and this embedding K and these other embeddings I0 and I1, so that each triangle commutes. And therefore, since I0 and I1 are ultrapower embeddings into the same model, they agree on the ordinals. So J0 and J1 are going to agree on the ordinals because they're just the same embedding composed with two ultrapower embeddings. So what this is really saying is that, at least under this singular Cardinals hypothesis, the difference between two elementary embeddings really reduces to the difference between two ultrapower embeddings. That's all there is to it. And then there's some other embedding comes out of it. So there's some category theory here, like a, I don't know, equalizer, co-equalizer. Okay. So that's the point. So this has a corollary, the thing we're trying to prove, the uniqueness of elementary embeddings. So some corollary under the ESCH, J0 and J1 from V to M, then J0 and J1 agree on the ordinals. And now the second thing that I want to do after the reduction under ESCH to the ultrapower case, the second thing is the reduction from the reduction to the ESCH case under ZFC, just not assuming anything except for lots of replacement and choice. So the point here, well, the idea is we're gonna assume towards a contradiction that we've got J0 and J1 from V into M that disagree on the ordinals. And the idea is, in this case, we'll prove that very large cardinals exist. So recall Solovey's theorem. If there's a strongly compact, some very large cardinal, then SCH holds above it. Or in other words, or some weaker fact, but the eventual SCH holds. So if we could prove there was a strongly compact, then we would get the eventual SCH, and that would be a contradiction because we could reduce to the previous case and get that, in fact, J0 on the ordinals did equal J1 on the ordinals. So this is a real serious proof by contradiction. You get basically no information in this second case. Okay, but we can't prove there's a strongly compact cardinal, but instead we're going to prove that there's something called an omega-1 strongly compact. I'll say something about it. Basically, omega-1 strongly compact cardinal kappa is a cardinal kappa such that every kappa complete filter extends to a countably complete ultrafilter rather than a kappa complete ultrafilter, which would make it strongly compact. So we'll prove there's an omega-1 strongly compact, and then Solovey's proof gives ESCH from an omega-1 strongly compact, and that's the contradiction. So we have ESCH, but we have two embeddings that differ on the ordinals, and that's impossible by the previous theorem.
Gabe, as an aside, do these omega-1 strongly compact cardinals have an elementary embedding characterization?
Yeah, they do. It's exactly like strongly compact, except you don't say anything about the critical point of the embedding.
Ah, I see. Okay.
So you say that you have covers of a set of size lambda that's of size less than J of kappa, where kappa is your omega-1 strongly compact, but you don't say that kappa is the critical point.
Okay, thanks.
Yeah. Okay, so what's left from this outline? Well, what do we have to do? We're left with one, the reduction to ultra powers, and under ESCH, and then to the reduction to ESCH. So I'm gonna fill in the details in the next 30 to 45 minutes. So let's start with one. So the issue that comes up in one has to do with the difference between an ultra power embedding and something that I'm going to call almost an ultra power embedding. So if J goes from V to M, then J is almost an ultra power embedding. If for any set A, so it's important that it's a set here, for any set A contained in M, there is some point A in M such that A is contained in the Skolem hull of the image of V plus the point A. So you can get any subset of the inner model M to be generated by a single point. To be an ultra power, you would need to get all of M to be generated by a single point. So this is a weak form of being an ultra power embedding. But so it's sort of like M looks locally like an ultra power, but globally it's not clear if M actually has to be an ultra power embedding. But it has lots of the characteristics of ultra power embeddings. For example, M has to be closed under omega sequences. That's going to be important. Okay. What the first thing that I'll show is that, well, I guess as a spoiler, under ESCH, almost ultra power embeddings are ultra power embeddings. And that's kind of the use of the singular cardinals hypothesis here. But the first thing I'm going to show is if you have your two embeddings, then you can find almost ultra power embeddings. There are almost ultra power embeddings, I0 and I1 from V to some inner model N, and an elementary embedding K from N to M with all the properties that we wanted before. So such that J0 is just K composed with I0 and J1 is K composed with I1. And then I'll show under ESCH that the almost ultra power embeddings are ultra power embeddings, and that gives the reduction to ultra powers that we wanted. Okay. So in proof, so you let H be the Skolem hull inside of M of J0 image V and J1 image V. So it's the smallest elementary substructure of M that contains the range of J0 and the range of J1. And since it's an elementary substructure, it's extensional, so let N be the transitive collapse. And okay, so what's going on? We have J0 and J1 M, and we had some hull here, H, and the transitive collapse N. So there's some embedding that witnesses that N is isomorphic to H, so that's an elementary embedding from N into M. So we're going to call that K. And then because the range of K is H, because K is an isomorphism from N onto H, so the images of J0 and J1 are contained in the range of K. And therefore you can pull back by K and get total embeddings, I0 and I1. So they're just defined by I0 is equal to K inverse composed with J0, and I1 is equal to K inverse composed with J1. So that the reason that these are total embeddings is that the range of J0 is contained in the range of K. And they're always going to be partial elementary embeddings. So what remains after this is to show that I0 and I1 are almost ultra power embeddings. So I'm just going to show that I0 is almost an ultra power embedding. The proof for I1 is the same. The point now is because we took this hull, we've ensured that there's basically a minimality property of I0 and I1. So that is just that N is the hull and N of the ranges of I0 and I1. And that's true just because H is the hull of the ranges of J0 and J1, and K is an isomorphism between N and H that moves I0 to J0 and I1 to J1. So that's how these things tend to work. So that's what we're going to use to prove that I0 is almost an ultra-power embedding. So fix set A contained in N, and I have to find point A, little a in N, so that A, big A, is contained in the hull of the image of I0 and the point A, little a. Okay, so need A, N, so that A is contained in the hull within N of I0 image V and A. Since we have this property, everything in N is definable from points in the image of V and points in the image of, points in the image of I0 and points in the image of I1. We can find a set B, or maybe I think I was calling it X before. There's a set X contained in V. It matters that it's a set, not a class. So I guess I can just, there's a set X in V such that A is contained in the hull within N of I0 image V and I1 image X. Because for each element of A, you can pick some X such that some finite sequence of points such that A is definable from I0 image V and those finite and I1 image of those points. So you just pick those points for every element of X, for every element of A, and that gives you your set X. So this is really just applying the axiom of collection. Okay, so we're just picking witnesses to the fact that this is true, but we only have to pick them for a set of A. So now it suffices to show that there's an A in N such that X is contained in the hull of I0 image V in the point A. Because then this contains this whole hull. Sorry, not X, I1 image X, sorry. Then this contains the whole hull, and in particular it contains A. So little a will be as desired. So we just need this, and that'll be easier. So take a set Y in V such that the cardinality of Y is equal to the cardinality of X, and I0 restriction Y is equal to I1 restriction Y. The way you can get a set like that is just you use the fact that I0 and I1 have a proper class of common fixed points. So you just take Y to be sufficiently large set of common fixed points of I0 and I1, and I0 and I1 have to agree on those ordinals. This is kind of the way that the local version, which would imply the HOD conjecture, just gets totally thrown out in this proof. But you can have a arbitrarily large sets of common fixed points. So that in particular gives you this. So let F be a surjection from Y onto X. Then we're going to set A equal to I1 of F, and that'll work. We'll get this. So the claim is that I1 image X is contained in the hull within N of I0 image V and the point I1 of F. So for this, just y fix an element x in x, then x is in the range of this surjection f, so x is equal to f of little y for some y. So I1 of little x is equal to I1 of f of y, which is equal to I1 of f of I1 of y, but that's equal to I1 of f of I0 of y, because we chose y so that I0 and I1 agree on every point in y. And now that means that, that I1 of x is in this hull. Because I0 of y is in the image of I0, and I1 of f was the point that we're allowed to use. So that gives you that for each x and x, I1 of x is in this hull, and therefore I1 image x is in this hull, contained in the hull. Okay, so that proved this lemma that basically that we almost have what we want. So if you have J0 and J1 from V to M, then there are almost ultra power embeddings such that everything factors. The problem is that it's not clear that almost ultra power embeddings is good enough to give you definable. If we knew they were definable, then it'd be done. And I haven't used the singular Cardinals hypothesis yet, but the way it gets used is in the following fact. So this proposition, I think, is comes from Kunin's original proof of the Kunin inconsistency theorem, which required using the GCH, really the SCH, but I don't know, it's abstract fact. That was never published. I just assumed that this is what he was doing because it uses the SCH. So what it says is, suppose J is an elementary embedding from V to M. You're not tired of hearing me say that. And M to the omega is contained in M. So M is closed under omega sequences. And assume the eventual singular Cardinals hypothesis. Then, well, have to introduce a little bit of technology. I'm avoiding using extenders just because some people don't like it. So I'm gonna have to say something before I say this. So we need one more elementary embedding invariant. So if J is an elementary embedding from V to M, and A is an element of M, then let lambda sub A be the cardinality, the least cardinality of a set X, such that A is in J of X. So this is the size of an ultra filter derived from J using A. But there are a lot of ways you can characterize it, like, so you can characterize it in terms of these hulls. So lambda sub A is equal to the minimum lambda, such that there is an F with domain lambda, such that A is in the range J of F. And so it's the minimum lambda such that A is in the hull within M of J image V and J of lambda. So each of these implications or equalities is very easy to see. One after another, it becomes extremely easy. Okay, so I'm gonna omit the proof, sort of. I mean, because I'm like sort of getting rid of all the extender theory, it makes it look like I'm doing really clever things, but really I'm just using a big theory that is developed, but not saying all the right words. Okay, so let's see. So what do I want to say? So another lemma is that if J is almost an ultra power embedding, it's an ultra power embedding if and only if the class of lambda sub a's for A and M is bounded. So I guess implicitly this lambda notation has to do with the embedding J. It's associated to J, but since we're no longer going to be dealing with more than one embedding at a time until later, it's not a big deal. So lambda sub A, if this class is bounded, then almost ultra is ultra. That's just, I mean, it's basically saying that if J is an extender embedding that's almost an ultra power embedding, then it's ultra power embedding, and the proof is really easy. So let lambda bound the lambda sub A's. Then for any A and M, A is in the hull of J image V union J of lambda, just by this characterization. So in other words, M is equal to the whole class M is equal to the hull of just this set J of lambda. And then since you're almost an ultra power embedding, you can approximate that set by just a point. So there's an A and M such that J of lambda is contained in the hull of just the point A. And so this whole hull is in, and so M is in. So M is the hull of J image V and the point A. So if this collection of cardinals is bounded, then and J is almost an ultra power embedding, then J is truly an ultra power embedding. So we just want to show that this is bounded. And then the point was almost ultra power embeddings are closed under countable sequences, and assuming this eventual singular cardinals hypothesis, if J goes from V to M and M to the omega is contained in M, then the class of lambda sub A's for A and M is bounded. So this is sort of an interesting lemma because it says if you have any omega closed elementary embedding, then in fact it's an extender embedding. So if the theory of extenders tells you that this means actually that J is automatically definable. So any elementary embedding from V into a countably closed model is definable under this hypothesis, which is sort of a weak hypothesis since it follows from large cardinals, strong large cardinals. So proof is, well, assume not, and then define a sequence A0, A1, A2 by recursion. So they're elements of M, so A sub N, M, to pick A0 so that the singular cardinals hypothesis holds above lambda sub A0, because we've got arbitrarily large lambda sub A's, so we can do that. And then 3, ensure that lambda sub A sub n plus 1 is larger than J of A sub n, lambda A sub n. So this is sort of similar to something that happens in the proof of the CUNY consistency theorem. If you look what's going on, you've got lambda A0, and it's mapping up to J of lambda A0, and then lambda A1 has to be above there, and then lambda A2 got to be above there. And if you let lambda be the supremum for n going to infinity of the lambda sub A sub n's, then it has to be that J fixes lambda. So basically we're making sure that lambda is a closure point of J using 3. And then because lambda has countable cofinality and J is continuous at ordinals of countable cofinality, J has to fix lambda. So points J of lambda is equal to lambda. Okay, so the way we'll get a contradiction is by looking at the sequence A of all the A sub n's, which by our assumption is an element of M, because M is closed under omega sequences. So we'll try to compute we'll show that lambda sub A is either lambda or lambda plus, and then we'll also show that that it's not. So first, to show that lambda sub A is either lambda or lambda plus. So the way that goes is, well, lambda sub A has to be greater than or equal to lambda sub an for each n, since A sub n is in the hull of J image V and A. So A is an omega sequence, so you just look at the nth point in that sequence, which implies that A sub n is in the hull in M, J image V, and J of lambda sub A. Since A vector is in there, and remember that lambda A sub n is the least such cardinal. So that means that lambda sub A vector is above lambda A sub n. And then lambda sub A vector is less than the product of the lambda sub A sub n's for n less than omega. Just fix A sub n such that, or I was calling it x sub n, such that A sub n is in J of x sub n, and cardinality of x sub n is equal to the lambda of A sub n. That's the definition of A sub n, is that you can find such an x sub n. I mean, the definition of lambda sub A sub n. And then A vector is in the product of the J of x sub n's, because each A sub n is in here, and A vector is a sequence of them for n less than omega, and that's equal to J of the product of the x sub n's. So A vector is now in J of a set that has cardinality, the product of the A sub n's. Okay. So that does this bound, and then because we assume the singular cardinals hypothesis holds above lambda A0, this is this product is equal to lambda plus. So it's like lambda to the omega, basically. And that's lambda plus times 2 to the omega, and we're way above the continuum. Okay. Then, so that shows that lambda sub a vector is between lambda and lambda plus, so it's one of those two cardinals. Now, we'll show that it's neither of them. So the fact that comes up is that if lambda sub a for any a you like is not 0, then j of lambda sub a has to be greater than the sup j image of lambda sub a, which is always greater than or equal to lambda sub a. The proof is just A is in the hull inside of M of J image V union J of lambda sub A, but for alpha less than lambda sub A, A is not in this hull of J image V union J of alpha. And so it follows that A is not in the hull M of J image V union the sup image of the alphas. So this supremum and this ordinal can't be the same thing because A is in this one, but not in this one. So that means the supremum. So a lot of this stuff is like standard large cardinal facts, but I don't know if they're really written anywhere. Okay. So yeah, the supremum is less than J of lambda sub A. I mean, it can't be greater, and they're not equal. Okay, next, that means that the issue now is that J of lambda is equal to lambda, so that says that lambda sub A vector can't possibly be lambda. It's greater than 0 anyway. And also J of lambda plus is what's equal to, by elementarity, the M successor of J of lambda, and that's just lambda. And this is the M successor of lambda, but that's less than or equal to lambda plus because an inner model can't have a larger successor of a cardinal than V does. So that gives you that J of lambda plus is equal to lambda plus or less than or equal. And that means that also lambda plus is not equal to lambda sub A vector. So that's the contradiction. Okay. So that shows omega closed models have bounded lambda sub A's, and therefore almost ultra power embeddings, which are themselves omega closed, are ultra power embeddings because their lambda sub A's are bounded. So that's a corollary under ESCH. Almost ultra powers are ultra. And so as a corollary under ESCH, we get the uniqueness of elementary embeddings. Okay, so that's the first half of the proof. That's actually the first 3/4 of the proof. And I don't know, should I continue? I mean, I can do the next part of the proof in like 15 minutes probably.
I think that would be fine if you could if you can do it in 15 to 20 minutes. It's great.
Okay. Thanks. Sorry. So the next part of the proof, remember, is the reduction to the singular cardinals hypothesis case, assuming just CFC. So the way this works, remember, was that we wanted to show if the embeddings didn't agree on the ordinals, there would be an omega-1 strongly compact cardinal. So remember, cardinal kappa is omega-1 strongly compact if every kappa complete filter extends to a countably complete ultrafilter. So the idea, well, then there's this fact, or this theorem, I guess, which is essentially due to solid A. It says that SCH holds, well, the eventual SCH, if there's an omega-1 strongly compact cardinal. Then the eventual SCH holds. One annoying thing about omega-1 strongly compact cardinals is that if kappa is omega-1 strongly compact, so is every cardinal above kappa. So it's really the least omega-1 strongly compact is like a threshold, and the other omega-1 strongly compacts are trivial in a sense. But okay, so if this threshold exists, then eventually the singular cardinals hypothesis takes hold. A weird thing about omega-1 strongly compact cardinals is that they can be singular. That's due to Magador and Vicaria who introduced these things. And they also proved, I think they proved that that in fact the singular cardinals hypothesis holds at the least omega-1 strongly compact, which could be singular. So that doesn't follow from solid A's argument. So that's their theorem. So let's see, but I only need ESCH anyway. So I want to get an omega-1 strongly compact from the failure of uniqueness of elementary embeddings. And the way I'm going to do that is using another theorem, essentially due to Kettinen. So there is an omega-1 strongly compact cardinal if and only if all sufficiently large regular cardinals carry uniform countably complete ultrafilters. So an ultrafilter on a set X is uniform if every set in the ultrafilter has the same cardinality as X. So this is saying that if there are big enough ultrafilters, or if eventually there are ultrafilters of every cardinality sort of, then there's an omega-1 strongly compact. I mean, when I say ultrafilters, I mean countably complete ultrafilters. So all we need to do is show that we have uniform countably complete ultrafilters on every regular cardinal. So just one more invariant of elementary embeddings. That is, I mean, it's just sort of useful notation. If J is an elementary embedding V to M, then the tightness of J at a set X in V is the minimum M cardinality of a cover of J image X. So the minimum M cardinality of a set in M that covers J image X. So it stands for tightness or something. So the useful thing about this, which is really easy to prove, but not immediately obvious, it only depends on the cardinality of X. Actually, this is a monotonically, even strictly increasing function of the cardinality of X. So the fact is, if the cardinality of X is less than or equal to the cardinality of Y, then Tj of X is less than or equal to Tj of Y. And the proof is sort of immediate. Let F be a surjection from Y onto X. Then if you have a cover of J image Y with A in your model M, then J of F image of A is a cover of J image X. It's in M, and the cardinality of J of F image A is less than or equal to the cardinality of A, because you've got this surjection. So that says that whenever you have a cover of J image Y, you can find a smaller cover of J image X. And so that's why the TJX is less than TJY. Okay, a useful thing about this though is, so the reason this comes up is that if J0 and J1 are elementary embeddings to the same model, then TJ0 is equal to TJ1. So this is like a uniqueness property of elementary embeddings, but it's really easy. So why? Well, so we want to prove, we just need to prove, since this is a function of cardinals, we just need that Tj0 of lambda is equal to Tj1 of lambda for all cardinals lambda. But take a set Y such that the cardinality of Y is equal to lambda, and J0 and J1 agree on lambda, on Y. Remember, just a bunch of fixed points. Then Tj of Y is the smallest cover of Y, of J image Y, J0 image Y. But I mean, that's the same as the smallest cover of J1 image Y, because J1 image Y is equal to J0 image Y. So these functions are the same. And it seems like you should be able to easily prove that J0 on the ordinals and J1 on the ordinals are the same given that, but I couldn't do it. I didn't try that hard because I like having a really complicated proof, but I tried a little bit. Okay, then once you know this, what I want to show is that if delta is regular and J0, so we're in this context where we have J0 and J1 into the same model. J0 of delta is not equal to J1 of delta, then delta carries a countably complete uniform ultrafilter. And it's just going to be derived from one of these embeddings. So okay. So how do you get it? Assume that J0 of delta is strictly less than J1 of delta. Then the point is that Tj1 of delta is strictly less than, or it's less than or equal to Tj0 of delta. I mean, it's equal to it. And that's obviously less than or equal to the sup J0 image of delta. Just because this ordinal obviously covers J0 image delta. And then that's going to be a lot smaller than J1 of delta, right? It's going to be smaller than this, which is smaller than this. So this cover is small. There's a small cover of J1 image delta, and that always is going to give you this existence of a countably complete uniform ultrafilter. The way you show that is, so I want to show the sup J1 image delta is strictly less than J1 of delta. And that's because the cofinality as computed in M of the sup J1 image of delta is at most the translation function J1 of delta, because that covers J1 image delta, and in particular it's cofinal in sup J1 image delta. So any cover of J1 image delta is going to cover J1, it's going to be cofinal in sup J1 image delta. So that means the cofinality is smaller than the translation function. In fact, they're always exactly equal, but that's not relevant here. And this is less than J1 of delta. And so that's equal to the M cofinality of J1 of delta, because delta is regular. So it follows that these two ordinals are not the same. They have different cofinalities. And hence, so that follows that the sup J1 image is strictly smaller. And now you can let U be the set of A contained in delta such that sup J1 image delta is in J1 of A. So the ultrafilter derived from J1 using sup J1 image delta. That's a uniform ultrafilter because no bounded subset of delta could possibly get this ordinal sup J1 image delta into J of it. It's always going to be bounded sup J1 image delta. So got a uniform countably complete ultrafilter on any disagreement point of J0 and J1. Now we just need to know that that all sufficiently large regular cardinals have uniform countably complete ultrafilter. So finally, we're proving this theorem, just the uniqueness theorem. If you have J0 and J1, d to M, they agree on the ordinals. The proof, so assume not, so we're saying, then fix alpha such that J0 alpha is not equal to J1 of alpha. Since these embeddings disagree, ESCH has to be failing. So there are arbitrarily, well, let's not even talk about that. Since the embeddings disagree, ESCH is failing, and therefore there is no omega-1 strongly compact cardinal, and I need to show there is one. So assume there is no omega-1 strongly compact cardinal. So get even deeper into this web of false assumptions. Therefore, by the Kentonen theorem, there are arbitrarily large regular cardinals delta that carry no uniform countably complete ultrafilter. So let delta be the alphath regular cardinal that carries no uniform omega 1 complete ultrafilter. By Ketenin, that has to exist. Look, J0 of delta is the J0 of alpha regular cardinal of M that carries no uniform countably complete ultrafilter in M. And that's strictly less than the J1 of alpha such cardinal. Or it's at least it's different from the J1 of alpha regular cardinal of M carries no omega 1 complete ultrafilter in M, because J0 of alpha and J1 of alpha are different. And therefore J0 of delta does not equal J1 of delta, which implies by what we just said that delta carries a countably complete uniform ultrafilter. Which it doesn't. So that's a contradiction because we assumed delta didn't carry one and proved it did. So that gives us our omega 1 strongly compact cardinal, which gives us the ESCH, which gives us that J0 on the ordinals is equal to J1 on the ordinals, which is a contradiction. So that's it. Okay.
Very nice. Thank you very much. That was great.
Thanks.
Great job, Gabe.
Awesome. Yeah, I guess maybe you can stop sharing. Okay, cool. Yeah, are there any questions? It was quite silent during the talk, but I feel like it was like an absolutely complete, totally lucid proof. Very nice. So are there any questions?
I have not really a question. I just want to make sure I didn't miss something along the way. In the first half or 3/4 of the proof, where you were using the eventual singular cardinal hypothesis, that part would have worked if you had eventual just about anything. It doesn't have to be just lambda plus. It was lambda triple plus or anything reasonably near lambda would be enough, right?
Yeah, that's true.
But since you get lambda plus in the second half of the proof, there's no point in doing that.
Yeah, another thing is that typically if it's reasonably close to lambda, basically below lambda plus the critical point of the embeddings that you're dealing with, then it actually has to be lambda plus because you get enough uniform ultrafilters to prove SCH using Solovay's theorem. So that's why, yeah, that sort of never helps or doesn't seem to. So all these questions get swept under the rug once you do this proof by contradiction, but like it's not clear whether there can be these almost ultra power embeddings that aren't ultra power embeddings or any of those kinds of extremely weird embeddings. But the proofs can't work. There's no way to make that proof work without the eventual SCH. There's some counterexample to the proof that is recent theorem Giddick.
Thank you.
Oh, sorry.
Yeah.
Gabe, do those lambda A's, do they have any kind of special name?
Unfortunately, they have many names, but not any special name. So lambda sub A is the cardinal lambda. It's the uniformity or the size of the ultrafilter derived from J using A. I don't know if
It's a cardinal. At first I thought maybe there were sets of cardinals, but it's a cardinal, right?
yeah, it's a cardinal.
I thought they were called, I felt like they were called spectrum, like a spectrum of something, but they're only just like a cardinal. At first I thought they were like a set of
Well, I
cardinals.
guess I guess the set or class of lambda sub a's would be the uniformity or the decomposability spectrum of the embedding J,
Hmm.
or it generalizes the decomposability spectrum of an ultrafilter. But yeah, there are lots of different names.
I think the issue may have been that when you wrote the definition of lambda sub A, and then you had two other characterizations of it in a lemma, the definition didn't actually have min in it. It just had lambda A equals.
Oh,
The
no.
lemma had min in both places, but I think that was causing the confusion here.
Yeah.
Slightly, yeah.
It's not a set of cardinals.
Okay.
The
It,
minimum-
it became clear, but okay.
Yeah, that was something I was confused about too. So your definition was that lambda A is the smallest cardinality of a set such that A is an element of J of that set, right? Is that?
Mhm.
Yeah. And then later at some point you assumed that you have an A and lambda A is greater than 0,
Oh yeah.
which seems like it should always be greater than 0 if that's the definition.
Yeah, so I should have said lambda A is greater than 1.
Okay.
Yeah.
Right. Yeah, that's what it seemed to be. Yeah. Okay.
There, I guess, is some conflict because there's an alternate characterization, which is that it's the least ordinal alpha, such that the set is in the hull of J of alpha, and I guess that doesn't quite work in the finite realm.
Right.
So that there's a tiny discrepancy in the trivial case where lambda sub A is either 0 or 1.
Yeah. I mean, essentially things that are already in the range you're not really interested in anyway. Yeah.
I could have said lambda sub A is bigger than 1. I messed that. I can't seem to get that quite right.
That's always the trivial things that are the most complicated.
I was trying to rule out a trivial case, but I
Right.
didn't quite do it. I was off by 1.
Okay, great. Any further questions?
Yes, Gunther, can I ask something?
Sure.
Gabe, very nice talk. So just one question. How exactly do you state the theorem? Because you said that if J0, J1 are definable, that's easy. You did that last time. So you're stating this in the language of ZFC plus 2 extra symbols for J0 and J1. And what about M?
Well, M is definable from J0 as the union of J's.
Oh, I see. Okay, so it doesn't matter. And then you have ZFC with the extra symbols J0 and J1, I guess each separately, but you don't need to have both of them, right?
You do.
Yes, because you want
You
common
do.
fixed points, right? I
Oh,
mean,
yes, so you want common fixed points. So, okay, so it's, you have 2 extra symbols, J0, J1, and you have ZFC in this expanded language, right? Okay.
But I'd sort of prefer to just work in second order set theory, so NBG.
Okay, fine, thanks.
Yeah, and there's sort of something interesting going on actually. Farmer Schlutzenberg pointed out to me that it's actually consistent to have a model of ZFC with 2 different amenable embeddings into the same inner model. So they're amenable classes of this model of ZFC, and they differ on the ordinals. The issue is that you don't have ZFC for both classes.
I see. And you needed it for the common fixed points, right? This is the...
Yeah, I may have used it more times than that, but maybe not.
Okay, very nice, thanks.
yeah, it seems like when you take this hull of the union of the ranges of J0 and J1 and you collapse that. Yeah. Okay. Great. Further questions? Okay, I think.
Look into the labor tables.
Okay. All right. Thanks a lot. It was a great talk.
Thanks for listening.
Gabe.
Technical.